Assalamualaikum and a very good morning. It's Abdullah bin Zaid Khairi and I'm from Group 4. We're presenting about atomic mass spectroscopy. Atomic mass spectroscopy is a versatile and widely used tool for identifying the elements present in samples of matter and for determining their concentrations. Nearly all the elements in periodic table can be determined by mass spectrometry. AMS offers a number of advantages over the atomic optical spectrometric methods, including the first one, the detection limit for many elements as great as 3 orders of magnitude better than optical method. Second, remarkably simple spectra that are usually unique and often easily interpretable. And the third one is the ability to measure atomic isotopic ratios. We will see further what is the mechanism of the detection of the isotopic ratios could be done later. However, AMS also do have disadvantages such as first, instruments that cost 2 or 3 times that of optical atomic instruments. Second, instrument drift that can be as high as 5% to 10% per hour. And the third one is there is certain types of interference effect that will be discussed later. In AMS, terms assigned for atomic and molecular masses play an important role and generally expressed in atomic mass units AMU or daltons dA. The dalton is defined relative to the mass of the carbon isotope, and this isotope is assigned a mass of exactly 12 AMU. Thus, the AMU or dA is defined as 1 over 12 of the mass of one neutral carbon atom. So we will see the definition and concept of AMS. AMS basically highlighted with 3 words, which is creating gas phase ions, separating the ions, and measuring the abundance of the ions. Because this is a technique where the gas phase ions was created from the molecules or atoms in a sample and then was separated the ions according to their mass to charge ratio m per z, and then measuring the abundance of the ions formed. This technique also provides both qualitative and quantitative information, such as mass of molecules and atoms in samples and the molecular structure of organic and inorganic compound. There are many types of atomic mass spectrometry depending on their atomic ion sources and typical mass analyzers, such as inductively coupled plasma, direct current plasma, microwave-induced plasma, spark source, thermal ionization, glow discharge, laser microprobe, and secondary ion mass spectrometry. Generally, AMS is a single focus mass spectrometer, means single magnetic sector is used to generate the magnetic field that differentiates ions according to their m per z value. The addition of an electric sector in a specified configuration provides a double focusing mass spectrometer that can achieve higher mass resolution than a single focusing mass spectrometer. So we will be moving to the principle of the AMS, but for my part, I will highlight about the inlet and gaseous ion sources. So in the inlet, the gas phase molecules from the sample inlet are ionized by a beam of high energy due to the high velocity of electrons that passing by closely among them. The rapidly changing electric field can both eject electrons from the atom or molecule due to ionization and transfer sufficient energy to the molecule to cause its bonds to rupture or fragmented. The ions are then accelerated in a an electric field at a voltage, the energy of each ion is equal to the charge times the accelerating voltage. The energy acquired by an anion on acceleration is kinetic energy. So it is important to note that the kinetic energy of an ion accelerated through a voltage depends only on the charge of the ion and the voltage, not on the mass of the ion. The translational component of the kinetic energy is equal to half of mv squared. The kinetic energy of all singly charged ions is the same for a given accelerating voltage. Therefore, those ions with small masses must travel at higher velocity than ions with the larger mass.
Good day. For this AMS presentation, I will present about the principle of electron multiplier. The most common detector used for ions in mass spectrometer is the electron multiplier, also known as the EM. The EM is very similar in concept to the photo multiplier tube for optical detection. It is very sensitive and have fast response. The EM is based on the dynode, which has a surface that emits electrons when struck by fast-moving electrons, positive ions, negative ions, or neutrals. There are two types of diodes, which are the discrete diode EM and the continuous diode EM. The discrete diode EM uses a series of 12 to 24 diodes, each biased more positively than the preceding diode. A collision releases several electrons from the diode surfaces. These electrons are then accelerated to a second such surfaces, which in turn generates several electrons for each electron that bombards it. This process is continued until a cascade of electrons or an amplified current arrives at the collector. Typically, one ion can produce 10 to the power of 5 electrons or more. This ratio of electrons measured per ion is referred to as the gain. The gain of the detector can be adjusted with operating gains of 10 to the power of 4 until 10 to the power of 8 used, depending on the application. Here I inserted a diagram. This is a schematic discrete diode electron multiplier showing the electron gain at each successive diode after impact of an ion on the first diode surface. The electron cascading process results in the gain of up to 10 power of 8 being achieved with approximately 21 diodes. I also inserted an ETP electron multiplier schematic that shows the position of the diodes in the detector. Next, we'll continue to the continuous diode EM. A continuous diode EM, also called a channel electron multiplier (CEM), uses a continuous glass tube, either lead doped or coated on the inside with a conductive surface of high electrical resistance. A potential difference is applied across the tube ends so that the potential varies in a linear manner along the tube. Each incident ion releases electrons that are accelerated and strike the tube again. This will result in the same cascade effect seen in the discrete diode EM. The curve or coil form is designed to reduce electrical noise by preventing positive ions from returning upstream. Here I inserted a schematic channel electron multiplier that consists of a glass or interior coated ceramic tube that emits secondary electrons upon ion impact. I also inserted a diagram. This is a schematic curve CM. The curved shape of the diode minimizes ion feedback noise. That's all from me. Thank you.
Assalamualaikum and hi, my name is Nur Azira binti Syari from Group 4. So, I will explain to you how ionization, fragmentation and separation occur in magnetic mass spectrometer. So, in the slide of 22, basically this is a magnetic mass spectrometer. We move to the next slide. So, in most cases, molecular ions have sufficient energy as a result of the ionization process to undergo fragmentation to form other ions of lower M to Z ratio. So, how ionization can be undergo? Ionization can be undergo with the rapidly changing electric field, which can both eject electrons from the atom or molecule and then transfer sufficient energy to the molecule to cause its bonds to rupture so that fragmentation can occur. So firstly, gas phase molecules from sample inlet are ionized by a beam of high energy, which is high velocity electrons passing closely among them. And then the ions are accelerated in an electric field with a voltage V. In this process, the kinetic energy is acquired by an ion acceleration and depends only on the charge of ion and the voltage. The kinetic energy of all singly charged ions is the same for a given accelerating voltage. So, the ions with small masses must travel at a higher velocity. And then they enter a curved section of a magnet of homogeneous magnetic field B and a fixed radius of curvature. This magnetic field acts on the ions, making them move in a circular motion. So, forces and energies associated with ions traveling through magnetic mass spectrometer. In order for an ion to reach the detector, centripetal force BZV must equals to centrifugal force mv squared over r. So, and then for the separation, as the basis of separation by M to Z, when V and B are kept constant, the radius of circular path depends on the M to Z value of the ionized molecule. So ions with different M to Z values travels in circles with different radii. And then, so when ions travel in different paths, from the figure, we can see there is the dotted line. So that is the path of the ions travel. So only one particular M to Z has the right R to pass through the mass spectrometer, while the others follow paths that can cause them to hit the sites and be lost. Basically that is for the magnetic mass spectrometer, but in modern magnetic mass spectrometer, the applied magnetic B is varied and voltage V is kept constant. The radius of curvature is a constant, so only ions with a trajectory of radius r will pass through. For a particular magnetic field strength, only ions with M to Z value that satisfies the equation will exit the chamber. The equation was as what has shown in the slide, which is M to Z equals to B squared R squared divided by 2V. And then as a result, for different values of B, ions with different M to Z will pass through the instrument to the detector, and then measure their abundance with a detector, which either counts and sums individual ions or measures a current produced by their impact on the detector. So that's all. Thank you.
Assalamualaikum, and my name is Siti Hawa binti Akadim. Today I will be talking about instrumentation that consists of ICPMS, also known as inductively coupled plasma mass spectrometry. Currently I wear mask because we are in COVID season right now. Prevention is better way, right? Okay. Let's get started. ICP-MS, a type of mass spectrometry that able in detecting metals at very low concentration. The detection it can detect as low as in PVT. It combines high temperature inductively coupled plasma ICP source and the mass spectrometer. The ICP source converts the atoms of element in the samples to ions. These ions are then separated on account of their mass that are detected by the MS. The patient source is ICP-MS. As we can see, it connected to the computer, so the mass spectrum can be print on this computer. So these components in ICP-MS. The sample is pumped into the nebulizer where it is mixed with argon gas to form an aerosol and it is passed through cold spray chamber. The final result then slide into the central channel of plasma. As it travels to high temperature plasma, the aerosol droplets will dry, decompose, atomize, and finally ionize, producing a rich source of positively charged ions. The ions are extracted from the plasma into the interface through the uh, sampling surface and through the skimmer cone through into the high vacuum region containing the ion lenses and mass analyzer. The electrostatic lenses focusedly at ion beam and separated positive ion from the unwanted neutral species by bending them into reaction cell, which the heart of the quadrupole reaction system. Here, the quadrupole allows only the high energy ions to pass through mass analyzer. So, only the target ions are stable and passes through axis of quadrupole. The quadrupole here scan rapidly across the mass range and passes each mass of the interest sequentially to the electron multiplier detector here. Ion strikes the detector and the resulting electronic signal are being processed and stored in multi-channel scanner, creating the mass spectrum where the intensity of the given mass is proportional to the concentration of the isotope at that mass. So, how ICP-MS works? As I said previously, the samples are introduced into an argon plasma as aerosol droplets. The plasma dries the aerosol, dissociates the molecules, and then remove an electron from the components, forming singly charged ions, which are directed into mass filtering device, which are mass spectrometer. Upon exciting the mass spectrometer, ions strike the first dimer of an electron multiplier, which serves as a detector. The impact of the ion release cascades of electrons, which are amplified until they become a measurable plus. The software compares the intensity of the measurable plus to those from standards, which make up the calibration curve to determine the concentration of the elements. Components in ICP-MS, which consists of sample introduction, ICP torch and RF coil, interface, vacuum system, ion deflection device, mass spectrometry, and the last one but not least, the detector. So this diagram is about ICP-MS in more detail, which shown as in the diagram, step by step. The first component in ICP-MS, which is sample introduction. The sample, mostly liquids, is necessary to break the liquid sample into small droplets before it can be introduced into argon plasma. It is introduced by peristaltic pump or through self-aspiration to a nebulizer that creates an aerosol of fine droplets. The fine droplets mostly are passed through a spray chamber before they allowed to enter the plasma. The desired end result to allow a considerable number of small droplets created by a nebulizer enter the torch and to discard the larger droplets, which can create analytical issue if it enter the torch. So basically, we just want the small droplets. The larger droplets, we discard it. The ICP torch and RF coil. The plasma generator in the ICP torch creates a very hot zone that serves a variety of functions. The temperature is approximately about 6,000 degrees Celsius. The plasma is generated by passing argon through a series of concentric quartz tubes that are wrapped by RF cord at one end. The energy supplied to the coil by the RF generator, also known as radio frequency generator, couples with the argon to produce the plasma. The liquid droplets containing the sample matrix and the elements to be determined are direct to solid and heated to gas. The atoms absorb more energy and eventually release an electron to form singly charged ions as they continue to travel through plasma. The singly charged ion exit the plasma and enter the interface region. The interface region link the atmospheric pressure ICP ion source to the high vacuum mass spectrometer. It allows both the plasma and the ion lens system to coexist. The ions generated by the plasma pass into the ion lens region. So it consists two or three inverted funnel-like devices called cones. There are two designs, which two-cone design and three-cone design, also known as hyperschema. The two-cone design requires downstream focusing of the beam that exits the interface region, provides two-step reduction in the pressure between the plasma and filtering quadrupole. The three-cone design is greatly reduce the divergence of the ion beam as it is in the interface region. It provides three-step reduction in the pressure between the plasma and the filtering quadrupole. So we can see here this two-cone design and this three-cone design. It has wide ion beam diversion, which means it large pressure reduction, while here we can see here it has small ion beam diversion, which smaller than two-cone design, so it has small pressure reduction. Next, in vacuum system, it provides high vacuum for ion oxide, quadrupole, and detector. It requires removal of nearly all the gas molecules in the space between interface and detector. It is accomplished using a combination of turbomolecular pump and mechanical roughing pump, which both comprise the main components of a vacuum system. So the turbomolecular pump works like jet turbine and capable rapidly pumping a chamber to pressure of 10 to the negative 5 torr or less, while mechanical roughing pump works by pump back the turbomolecular pump and evacuate the interface region. So the fifth component in ICP-MS is ion deflection device. It guides the desired ion into the quadrupole analyzer while assuring the neutral species and photons are discarded from the ion beam. A quadrupole is typically used as mass filtering device where the ions travel in path parallel to the roots. Here, when a quadrupole is placed at a right angle to the ion beam and immediately between interface region and the filtering quadrupole, ions can be efficiently transmitted while the neutron and photons are readily removed from the ion beam. So we move to the most important component in ICP-MS, which is mass spectrometry. Mass spectrometry is used to identify and determine the elements present in samples and to determine their concentration. It's also to measure the relative atomic mass of an element and measure the relative molecular of substance. Mass spectrometer act as mass filter to sort ions by their mass to charge ratio and per Z. There are three main types used in ICP-MS, which are quadrupole, time of flight, and magnetizector. quadruple is commonly used in most laboratories because it works by setting the voltage and radio frequency to allow ions of a given mass to charge ratio remain within the rods and pass through the detector. Under the control of instruments software, the MS can move to any MZ needed to measure the elements of interest in the sample analyzed. For example, to measure sodium, which has a single isotope at mass 23, the MS can be set to allow the ions with MZ 23.1 to pass. So here in mass spectrometry, they are consist of 4 steps. The first is ionization, the second accelerator, deflection, and the last one is detection. So, in stage 1, which ionization, the common type used is electron ionization. Sample is bombarded by electrons which come from a heated filament. The electrons runs in a stream between the cathode and anode. When the sample passes through the electron stream, the high energy of electron in the stream knock electrons out of the sample to form ions. In second step, which is acceleration, is a simple step where ions are placed between a set of charged parallel plates. The ions will then be repelled by one plate and attracted to the other. There is a slit cut in the plate which the ions are attracted to. The force of attraction and repulsion forces the ions through the slit at an accelerated rate. The speed of acceleration can be adjusted by changing the charge of the plates. In the deflection, ions are deflected by magnetic fields surrounding the instrument. The amount of deflection depends on the mass and charge of the ion. The heavier ion and 2 plus or more positive charge ions are deflected the least, which you can see here, the heavier one. The lightest ion and 1 plus ions are deflected the most in ion stream A. Here is for the lightest one. While the ion stream B, here, it is the ions at the correct mass and charge travel the detector, which means in ion stream B, it will move directly to a detector. The mass to charge ratio MZ is determined from the ion that hits the detector. In the last step, which is detection, occur when the ion stream reach the detector, they hit a wire. By hitting the wire, they become neutralized by an electron jumping from the metal wire to the ion. The amplifier picks up the current that being created between the wire and the ion and amplifies the signal detected. The computer will pick up this and convert it to MZ and a spectrum is produced. We can see this the mass spectrum produced. In detector, it counts the individual ions exiting the MS. The ions exiting the MS strike the active surface of the detectors and generate measurable electronic signal. The active surface of the detector dioide releases an electron each time an ion strikes it. The ion exiting the MS strikes the first dioide, which releases electron and starts the amplification process. The electron release strikes a second dioide where more electrons are released. This cascading of electrons continues until a measurable pulse is created. By counting the pulse generated by the detectors, the system counts the ion that hit the first dioide. So, here is about the elements that can be analyzed using ICP-MS. So, we can see clearly from the periodic table that almost all the periodic table elements can be measured using ICP-MS except for the pink one and the red one because it's not unmeasurable and unstable element. the ICP-MS can be performed on solid and liquid sample, but the solid sample must be converted to liquid before testing by dissolving the sample into a solvent, which typically acid, to produce a solution before we can use it in ICP-MS. That's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Najwa binti Muhammad Madani. I'm the one of the member of Group 4 to present about the AMS, atomic mass spectrometry. So my part is about how to obtain mass spectrum. So this page will describe how a mass spectrum is produced using a mass spectrometer. So in fact, there are several different designs of mass spectrometer which differ in detail. So oh, sorry. Okay. So this one is a component of the mass spectrometer, which is there are have inlets, goes to the gases ion source, and go to mass analyzer, go through the ion transducer, and last signal processor. So end up to produce mass spectrum. Okay, so we know that the mass spectrometer is an instrument that produces ions and separates them according to their mass to charge ratio. Most of the ions we will discuss are singly charged, so that the ratio is simply equal to the mass number of the ion. Alright, next I will explain about the block diagram in the figure 11.1, and I will explain about the purpose or the function of the component of a mass spectrometer. So we go first with the inlet. The purpose of the inlet system is to introduce a micro amount of sample into the ion source, where the component of the sample are converted into the gaseous ions by bombardment with the electrons, photons, ions, or molecules. Alternatively, ionization is accomplished by applying thermal or electrical energy. So the output of the ion source is a stream of positive or negative gaseous ions that are then accelerate into the mass analyzer. Next, the function of the mass analyzer is analog to the monochromator in an optical spectrometer. In a mass analyzer, however, this function depends on the mass to charge ratio of analyzed ion rather than on the wavelength of photons. Like an optical spectrometer, a mass spectrometer contains a transducer that converts the beam of ions into an electrical signal that can be processed, stored in the memory of the computer, and displayed or stored. Unlike most optical spectrometers, mass spectrometers require an elaborate vacuum system to maintain a low pressure in all of the components except the unlike the most optical spectrometers, mass spectrometers require an elaborate vacuum system to maintain a low pressure in all of the components except the signal processor and read up. Low pressure ensures infrequent collision in the mass spectrometer to produce and maintain free ions and electron. So this one is type of atomic mass spectrometers, AMS. So we know that I must explain about this before. Then the ion source, we have inductively coupled plasma, microwave induced plasma, DC glow discharge, RF discharge, and so on. So meaning. So sorry. Next, this one's mass analyzer. So that is the three types that are used in atomic mass spectrometry, which is the quadruple mass spectrometer, the time of flight mass spectrometer, then the last one is the double focusing mass spectrometer. Other type of mass spectrometer are considered in this picture. Like another one, Fourier transform mass spectrometer, quadruple ion trap. So magnetic sector mass spectrometer also include in this one, mass analyzer. So that is my part. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Saya Muhammad Iqbal Ismail daripada grup KAT345 Atomic Mass Spectrometry AMS. Saya akan menerangkan tentang interferences of isobaric polyatomic ion interferences dengan oxide and OH species, serta dengan interferences of metric effect. Untuk part isobaric, kenalkan dulu. There are two main types of interferences, isobaric dengan polyatomic ion interferences. Isobaric interferences ni merujuk kepada elemen yang berbeza, yang mana isotopnya berkongsi common mass. Manakala polyatomic interferences adalah hasil daripada kombinasi dua atau more isotop from different elements. Isobaric, satu sumber ion yang generate or chemical species akan mengalami plurality of isotop. Maksudnya isotop mereka akan jadi banyak. Transmisi ion tu akan sungkuran menghadapi satu gas reaction yang capable untuk membentuk molekul edak dengan chemical species. Transmisi ion juga bila dia masuk dalam mass analyzer dengan mass analyzing punya part, ion dia boleh determine ratio yang akan signifikan balik pembesaran isotop chemical untuk tengok apa interference yang ada. Sebab kita nak obtain a set of isotope reaction. Kalau kita compare isotope reaction profile in the set, determination of isotope reaction profile adalah berbeza daripada reaction yang lain, sebab dia tunjuk sebab dia tunjuk benda lain lah. Proximate ion interferences. Ini sebenarnya paling problematik sikit lah dalam AMS. Proximate ion ni membentuk plasma yang bersuhu tinggi, sama ada sebabkan atomization yang tidak complete ataupun recombination of atom semasa extraction from the mass spectrometer. Oxide and OH species. Oxide NMO, doubly charged species can be, dia bila cakap pasal oxide and OH species ni cakap pasal MO plus dengan MO minus punya species. Conventional external calibration method was applied, and using analytical IFS ratio, one can minimize the contribution of the interfering ion to the analytical signal and improve accuracy. Oxide MO minus, MO plus and doubly charged species M2 plus can be significantly reduced through proper tuning of the plasma and touch condition by good plasma design. MO plus level, MO plus level, dia direct proportional lah, maksud dia straight slope macam tu, to the metric based interferences such as those derived from chloride and sulfate materials. This thus a low level of MO plus, typically CEO atau CE, measured since the COO bond is very strong and CEO is stable in the plasma, and it's a highly desirable property in ICP-MS instrument. Matrix effect interferences pula ada dua basic kategori, iaitu matrix induced spectral overlap dan matrix induced signal intensity change. Secara umum high concentration of matrix element results in the suppression of analyte signals. And then the degree of the matrix effect is strongly dependent on nebulizer flow rate and tends to be less severe than low nebulizer flow rates than at high nebulizer flow rates. Maksudnya degree while separation effect can seem most general, ianya boleh berlaku. Kita akan nampak enhancement, particular at high nebulizer flow rates. Plasma flow power and sampling depth does not appear to have a major influence on matrix effect. The main cause of the observed matrix effects appears to be disturbance of ion beam path through the ion optics and the mass spectrometer by the high concentration of matrix element.
Next is how to overcome the interference and thus increasing efficiency of the solution. There are several ways to overcome the interference. One of the way is using high resolution ICP-MS or HR-ICP-MS. In the case with high resolution molecular mass spectrometer, this magnetic sector of TOF based instruments permit accurately mass determination. Quadruple system are limited to unit mass resolution. Therefore, the use of HR-ICP-MS eliminates many of the spectral interference seen with quadruple because the overlap do not occur. The resolution is sufficient to separate the exact masses of the polyatomic species and analyte elements. HR-ICP-MS is the only way to measure accurately low level of elements that suffer from significant interference, including sulfur, phosphorus, silicon, fluorine, and chlorine. HR-ICP-MS allows interference to be characterized using exact mass measurement. For the second way, we use the collision and reaction cell. A collision cell is often a small hole or quadrupole insert between the ion optic and the mass analyzer of the instrument. As the ions, including polyatomic ions, pass through the cell, they are bombarded with gas molecules, usually helium or hydrogen. The collision breaks apart the polyatomic ions, greatly reduce their number. The dynamic reaction cell, or DRC, from Perkin-Elmer use specific gas phase chemical reaction to greatly reduce polyatomic interference. The DRC eliminate polyatomic interference using ion molecule reaction. The gas phase ion molecule reaction convert the interferent ions into non-interference product. That's all for me. Thank you.
Hey, my name is Muhammad Faisal, and I'm going to talk about a case study of determination of lipid A and endotoxin in serum by mass spectrometry. The objective of this case study is to determine lipid A content of endotoxin added to serum by combined gas chromatography mass spectrometry, and the second one is to make the metal esters and to extract the fatty acid produced on hydrolysis of serum containing lipose polysaccharide. The last and but not least is to separate metal ester of hydroxy fatty acid from other fatty acid metal esters using silica gel chromatography. Introduction. Mass spectrometry has been used successfully in the past to detect various biological compounds. A method to detect endotoxin in serum by quantitating beta-hydroxymellic acid by means of gas chromatography by mass spectrometry is developed by the researcher, and it is highly specific and very sensitive. The method described in this communication quantitates nanogram quantities of lipid A and endotoxin in serum. The procedure of determination of myristic acid content of lipid A. R595 lipid A or E. coli 0127 B8 endotoxin is measured in 5 ml of pyrogen-free 0.85% of weight per volume sodium chloride, or in 3 to 5 ml of rabbit or human serum, were hydrolyzed with 5 ml of 8 molar hydrochloric acid for 4.5 hours. The free fatty acid of the hydrolysate were extracted 3 times with 10 ml of diethyl ether. The ether extract were washed with 5 ml of pyrogen-free water and dried under liquid nitrogen. The extracted free fatty acid then were methylated, dried under nitrogen, dissolved in 0.5 ml of pentane, and applied to a dry silica gel column. Then 0.25 ml of trimethylsilyl is added. The samples were shaken on a vortex mixer. After 2 minutes, 1 ml of water was added. The Me3 silica ether of hydroxy fatty acid metal ester were extracted 3 times with 1 ml of pentane. The pentane extracted were pulled and dried carefully under a nitrogen stream. The dried Me3 silica ether were dissolved in 0.1 ml of acetonitrile, mixed on a vortex and filtered through passive pipettes plugged with selenized glass wool. 2 to 5 microliter of the acetonitrile solution were injected into gas chromatography mass spectrometer. The relative abundance of 315.4 atomic mass unit was determined by using a selected ion monitoring program in conjunction with 6 ion data acquisitions program available from Hewlett-Packard. The procedure of extraction and separation of serum lipid. 3 ml of serum were extracted with chloroform, methanol, and water with ratio of 8 to 4 to 3 volume per volume respectively.
The aqueous extract was removed and washed with chloroform. The organic phase was removed and dried under nitrogen. The lipid was separated by silica gel column chromatography with chloroform, acetone, and methanol as eluting solvents. The eluted lipid and the remaining silica gel were dried and used for further analysis. The extraction of lipid A. As Minnesota R595 was grown in beef extract broth, harvested, washed twice with water, treated sequentially with ethanol, acetone, and ether, and dried under reduced pressure. The glycolipid was extracted by the method of Galanos C. Luderitz was obtained by hydrolysis with 1% acetic acid. The results of separation of methyl ester of beta hydroxy fatty acid. As you can see, there's three major peaks were related with methanol as solvent, as shown in figure 2a. The first measure at 5.2 minutes coincide with the elution time of beta hydroxy methyl myristate. Increasing the ether content of pentane to 20% resulted in the quantitative elutions of non-deuterate methyl esters, as shown in figure 2b. Methylated serum extract to which no non-deuteric methyl ester was added, there appeared to be a small peak in the 20% ethyl eluate. The figure 2a shows as serum extract plus non-deuteric methyl acid, while figure 2b shows 20% ester eluate of serum extract plus non-deuteric methyl esters. The result observed compared to theoretical ratio of pentadeuterate to non-deuterate derivative, there was a direct correlation of theoretical and observed ratio. As shown in figure 3, the observed ratio is always less than theoretical ratio. This is due to the fact for equivalent amounts of non-deuterate and pentadeuterate derivative, higher abundance is obtained for the non-deuterate derivative, as shown in figure 1. The result of beta hydroxy myristic acid content of lipid A and endotoxin. The data indicate that the abundance at 315.4 is approximately 10-fold higher for lipid A than an equal amount of endotoxin. A linear relationship between abundance at 315.4 and increasing amount of lipid A and E. coli endotoxin, as shown in figure below. Of beta hydroxy fatty acid content of normal, human, and rabbit serum. 3 peaks at 315.4 atomic mass unit were detected in both the rabbit, which is in the right hand side in the figure above, and human in left hand side in the figure above serum. The first peak eluted correspond to the retention time observed with the pentadeuterate internal standard, while peak 2 and peak 3 have not been identified. The result of origin of beta hydroxy fatty acid in control serum. Normal rabbit serum is separated into aqueous and lipid soluble fraction to determine if the beta hydroxy fatty acid would derive from circulating endotoxin, lipid A, or other lipids. Further fractionations by silica gel chromatography show that over 80% of the hydroxy fatty acids are eluted with acetone or methanol. This strongly suggests that beta hydroxy myristic acid seen as gas chromatography mass spectroscopy of normal sera are eluted in the acetone and methanol fraction are not derived from endotoxin or lipid A, but from other circulating lipids, probably from phospholipids. Lipid A was found to be quantitatively absorbed by silica gel and not eluted with chloroform, acetone, or methanol. Discussion. The determination is based on hydrolysis of serum followed by analysis of total amount of beta hydroxy fatty acid. Separation of normal rabbit serum into lipid soluble and water soluble fraction indicate that most of the material contributing to 315.4 abundance in normal serum are lipid soluble. On silica gel chromatography, over 80% of these substances, giving 315.4 abundance, were eluted with acetone and methanol, and it strongly suggests that phospholipid are the compounds primarily responsible for the 315.4 abundance in normal serum. The abundance at 315.4 does not appear to be directly derived from endotoxin or lipid A. Less than 5% of the 315.4 abundance is found in the aqueous phase of chloroform, methanol, and water ratio. Extract of normal rabbit serum, and this is due to low level of undetected endotoxemia. The sensitivity of the procedure described could be improved by first removing serum lipid prior to analysis for endotoxin. Second is to concentrating the Me3SI-Me beta hydroxy C14 derivative to 10 microliter rather than to 100 microliter. This modification will permit detection of endotoxin at less than 1 nanogram per milliliter of serum. The large amount of unsaturated and saturated fatty acid injected in conjunction with the relatively small of beta hydroxy fatty acids results in the shutdown of mass spectrometer detector due to excess source pressure. Hence, complete removal of saturated and unsaturated fatty acid metal ester by silicic acid chromatography is essential to detect small amounts of beta hydroxy fatty acid metal ester.
Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Fairumati Azizan. Okay, for my part is I'll present about ion transducer, signal processor, and vacuum pump. Okay, for first is ion transducer or equal detector. The function is to convert the beam of ion into an electrical signal that can be processed, stored in the memory of the computer, and displayed or stored. It detects ion and recording relative abundance of each resolved ionic species. There are several types of ion transducer, which is electromultiplier, Faraday cup, and Iris transducer. Faraday cup is made from a metal or a carbon cup. It is less expensive. The function is to capture ion and store the charge. The resulting current of a few microampere is measured and amplified. The cup shape of a Faraday cup decreases the loss of electron from the metal due to ion impact. It also can be used to calibrate the other detectors. The current is directly proportional to the number of ions and the charge per ion collected by a detector. It does not exhibit mass discrimination. It has longer time to respond, which is limit its utility. It used for making accurate measurement in isotope ratio mass spec, where the ion current don't change rapidly. It has no gain associated with it, unlike diode-based detectors. It limits the sensitivity of the measurement. High precision isotope ratio mass spec are designed with multiple Faraday cup and multiple miniature of electromultiplier, which is referred as ion counter for simultaneous isotope measurement. For example, is Triton and Neptune multi-collector mass spec from Thermoelectron Corporation. It can be configured with up to 9 Faraday cup and 8 electron multiplier. The function is to detect 17 beams simultaneously. Multi-collector instrument used to improve precision by 2 to 3 orders of magnitude over single collector magnetic sector instrument. The next is Iris transducer. From the figure I put above, It positioned in the focal plane of a mass spectrometer. It provides several significant advantages over single-channel detection. Most important is the simultaneous detection of multiple resolution elements. It improved precision using ratio measurement and internal standard. It also improved detection of fast transition signal. One type of array sensor which commonly used is microchannel plate. The key element in electrical optical ion detector is microchannel electron multiplier, which is the layer inside the electrical optical ion detector. From the image given, the metallic electrodes are deposited on both sides of array. Voltage about 1500 voltage is applied between the end of channels. The tiny channels, which are oriented at the small angle from the normal of array surface, are individual electron multiplier. Particle that striking the inner surface of channel cascade through the channel and produce about 1000 of electron for every incoming particle. In AIOD, a phosphorescent screen is placed behind the microchannel plate, which is given on the figure above, so that the cascade of electrons produce a flashlight that directed to an optical array detector via fiber optic. The data collected for array detector then provide two-dimensional of ion appearing at the focal plane of mass spectrometer. And then next is signal processor. Signal processor is a computer which rapidly collect, digitize, normalize, and process current ion data from detector along with background subtraction. It converts the output into the system into a mass spec and key data for mass spectrometric analysis. The next is vacuum pump. It used to maintain the low pressure in all components except the signal processor and readout. This is to ensure the frequent collision in the mass spectrometer to produce and maintain the free ion and electron. It allows ion to reach detector without colliding with a molecule and to increase the resolution and sensitivity. Thank you.